All right, let's dive into one of the most game-changing technologies on the horizon, quantum computing. Now, on one hand, it promises to solve some of humanity's biggest problems, but on the other, it carries a threat that could literally break the digital world as we know it. So, let's get into it. And no, that's not some far-off hypothetical. In late 2024, Google's Willow quantum processor did exactly that. A calculation that would take a normal supercomputer longer than the entire age of the universe was done in the time it takes to make a cup of coffee. That's the staggering, almost unbelievable power we're talking about here. So, how is this even possible? Well, it all comes down to a totally different way of processing information. You see, the computer or phone you're using right now uses bits. They're basically tiny switches, on or off, 0 or 1. Simple. But quantum computers, they use qubits, which play by the wonderfully weird rules of quantum mechanics. And that brings us to the first quantum superpower, superposition. Think of it like this. A classical bit is like a light switch. It's either on or off. A qubit, though, is more like a spinning coin. Until it lands, it's both heads and tails at the same time. This means it can explore tons of possible solutions to a problem all at once, giving it this incredible computational edge. The second superpower is something called entanglement. And honestly, this is where things get really wild. When you entangle two qubits, their fates are linked. If you measure one, you instantly know the state of the other, even if it's on the other side of the galaxy. But here's the mind-blowing part for computing power. Every time you add just one more entangled qubit, you double the system's entire computational space. That's the secret sauce to its exponential power. So why are we doing all this? Well, this incredible power isn't for making your video games run faster. We're talking about designing new medicines by perfectly simulating molecules, creating revolutionary new materials, and solving massive logistics problems that are just impossible for the supercomputers we have today. Okay, so with stakes this high, it is absolutely no surprise that building a working quantum computer has sparked a global race. Let's take a look at who's building what and how they're doing it. You know, there isn't just one way to build a qubit. Right now, it's kind of the Wild West, with a few different technologies competing. On one hand, you've got superconducting qubits, which Google and IBM use. They're super fast, but you have to cool them to temperatures colder than deep space. Then there are ion traps, which are incredibly stable and accurate, but a bit slower. And new approaches like neutral atoms and photonics are showing huge promise for scaling up and maybe even working at room temperature one day. In this race, you can kind of think of the US approach, led by folks like Google, as the Tortoise. Their new 105-qubit Willow chip is a huge deal, not just for its size, but because it's showing that quantum error correction can actually work. In other words, they're proving you can build bigger systems that are more reliable, not less. They're absolutely playing the long game. And then, of course, you have the Hare. Researchers in China also have a 105-qubit processor, the Zuchongzhi 3.0. Their focus? Raw blistering speed right now. On one specific task, they claim it performed 1,000,000 times faster than Google's latest machine. It's a different strategy, focused on pushing the absolute limits of computational power. Meanwhile, Russia is taking this really unique and frankly clever approach. Instead of using simple qubits that can be 0 or 1, their scientists built a processor where each ion can be in one of 7 different states at once. They call it a qusept. This incredible information density means their 26-ion system actually performs like a 72-qubit machine. It's a perfect example of achieving more with less. The bottom line is the pace of this race is just nuts. In just over a single year, we've seen massive breakthroughs from the US, China, Russia, and Europe. Everyone is pushing the boundaries in a slightly different way, which makes this a truly neck-and-neck competition. But all of this amazing computational power has a really concerning dark side. It poses nothing short of an existential threat to the very foundation of our digital security. Here's the crucial point. The encryption that protects our bank accounts, our government secrets, pretty much all online communication, it's all based on mathematical problems that are just too hard for normal computers to solve. But for a powerful quantum computer, those hard problems become trivial. And there are two main culprits. First, there's Shor's algorithm. It's basically designed to crack the kind of encryption, like RSA, that protects almost all secure internet traffic. It's toast. Then you have Grover's algorithm, which takes on symmetric encryption, like AES-256. It doesn't break it completely, but it makes it a lot weaker, effectively cutting its security strength in half. Now you might be thinking, okay, that's a problem for the 2030s, but you'd be wrong. The threat is active today. There's a strategy known in the intelligence world as harvest now, decrypt later. Here's exactly how it works. Right now, adversaries are hoovering up massive amounts of encrypted data. They can't read it yet, but they don't have to. They are just storing it on huge servers, waiting. They're waiting for that one day when they finally get their hands on a powerful quantum computer. And when that day comes, all of today's secrets will be wide open. So, if quantum computers are coming and they're going to break our current security, what on earth do we do? Well, just as there's a race to build a quantum computer, there is an equally urgent race to defend against one. The main solution is a whole new field called Post-Quantum Cryptography, or PQC for short. These are brand new types of encryption algorithms. They're built on different, super complex math problems that we believe are incredibly difficult for both classical and quantum computers to solve. And listen, this isn't just some theory. The global switchover has already begun. In August 2024, the U.S. Standards Agency, NIST, published the first ever official standards for these new quantum-resistant algorithms. That's the starting gun for governments and industries to start upgrading their security. So the race is on. The general consensus is that we'll hit quantum utility, the point where these machines get really useful for science, by 2030. And the arrival of a machine powerful enough to break today's encryption, that's predicted for sometime between 2030 and 2035. The clock is definitely ticking. Which brings us to the final and most critical question. This tech is no longer science fiction. It's a monumental opportunity for sure, but it's also a systemic risk to everything we do online. The plans to harness its power, and just as importantly, to defend against its threat, need to be happening not in the next decade, but right now. So the real question is, are you ready?